Okay, great. Well, yeah, let me see. Maybe I should, before I share the screen, actually it'd be easier if I could see everyone, but yeah. So I just wanted to say, I've known Mignon since, I was a postdoc actually at the University of Arizona from in 1999. So I guess that's 25 years now. It's about that long that I've been working on things related to this talk, but Mignon and I had a sort of shared interest in P1 minus 3 points. And well, yeah, actually with him, I was learning about quasi-triangular, quasi-algebras, but don't ask me what one is. Um, so, I've always sort of been in awe of Mignon as a scholar of just like incredible breadth. I mean, he basically knows something about everything. And I've seen him, I don't know, debate scholarly takes on evolution in a car, and at many uh, dinners at Merton College, quiz economists, physicists, and probably art historians on delicate questions in their respective areas. So so he brings the same breadth of interest to his math, and uh, it was already clear to me back in Arizona that how what an incredible mathematician Mignon is, and so I've been honored to have him as a colleague all these years. So now today I'm just going to talk about Eisenstein cocycles, which I've been working on for a few years now. So let me get to some background for that. So so I guess the first connection between sort of GL2 over Q and GL1 over Q came through Ribot's converse to Herbrand's theorem. And so just to remind you, that says that if P is an odd prime and K is a positive even integer, and A is, let's say, the P torsion in the class group of the P cyclotomic field, well, then, on this class group, we have an action of the Galois group of Q mu P over Q, and we can single out the part on which, the Galois group acts by a given power of the cyclotomic character. Let's take the 1 minus k. And so that doesn't vanish if and only if P divides a certain Bernoulli number, BK, or actually BK over K. In other words, the valuation is at least 1. So Ribot showed that if P divides this Bernoulli number, then this isotypical component of the class group doesn't vanish. And the way he did this was to, well, notice that, this BK over K is the constant term of a Eisenstein series in essence, up to a factor of -0.5. And there's a mod P congruence in this case between this, say, this weight K Eisenstein series with this constant coefficient and a cusp form, but not just a cusp form, an eigenform. And so associated to this eigenform, there's a Galois representation, and which is in this case residually reducible. And if you choose a good lattice in this Galois representation and you reduce it mod P, then he was able to find this sort of unramified outside P extension, unramified extension of Q mu P he was looking for in the fixed field of the kernel of this residual representation. Now, so that's sort of a curious connection where the geometry of modular curves is already sort of influencing the arithmetic of these sort of cyclotomic fields. Cyclotomic fields being abelian extensions of Q, I think of them as sort of GL1 objects. So I want to describe a different connection between modular curves and cyclotomic fields, which is actually related to this other connection, but is sort of going in the opposite direction. Sort of in the form of like Eisenstein maps. So that's this philosophy here. So there's a map from the first homology of a modular curve to the second K group of a cyclotomic integer ring. And the second K group, say Q mu P, when I reduce it mod P, it's actually isomorphic to the P part of the, so let's see, if I tensor it with ZP, I take the P part of the K2 of the cyclotomic field, it's isomorphic to the P part of this class group of Q mu P. The Galois action differs by a twist, but sorry, it's isomorphic mod P. Okay. Anyway, so this is a connection between the topology of this map from homology gives me a connection between the topology of GL2 and the arithmetic of GL1. So I want to explain this particular case, and then I want to explain how the method which allows one to show this allows one also to give other instances of this sort of connection. Okay, so let me talk about the map more specifically. So we could take the homology of the modular curve x1 of n relative to its cusps. It has a very simple presentation, which I've written here, on generators U and V for relatively prime U and V mod n, which are known as Monin symbols. And yeah, so that has these just two relations, I guess, this group. Here, the Monin symbol is a geodesic in the upper half plane from the cusp, say, B over D to the cusp A over C, where ABCD is a matrix in SL2Z, where C and D are U and V mod n. Okay, so you pick such a matrix, you form the geodesic. It actually only depends upon C and D mod n, and that gives you, these things together generate the homology of the modular curve. So on the other hand, we also have symbols in K2. So if I look at the K2 of the cyclotomic integer ring of Q mu n, so or the n integers, so I'll invert n, then it contains Steinberg symbols, which are pairs of cyclotomic units, 1 minus zeta n to the u and 1 minus zeta n to the v, where zeta n is a primitive nth root of unity, so that obviously only depends upon u and v mod n. And this is, so these Steinberg symbols in K2 actually come from a product structure on the, in K theory, K1 of this integer ring is the units in that ring. And so much as with K groups of fields, these K2 of the integer ring satisfies the Steinberg relations. If I have two units, x and 1 minus x, they both have to be units in this ring, which is a fairly strong condition, then they pair trivially. Okay, so let me move on. And feel free to ask any questions. Okay, so the map that was defined sort of independently by Buziok and I in 2007 is a map from, you know, this homology to K2, which sends the Monin symbol to the Steinberg symbol. You notice the way I defined it here is I allowed U and V to be 0. If I don't want to allow U and V to be 0, I just have to use certain cusps. But if I want to include all cusps, homology relative to all cusps, then I'll just send the remaining symbols to 0. Okay. And so here, to make this map sort of a well-defined homomorphism, we need to take fixed parts under complex conjugation, which hence the plus. And what I'm really interested in, though, is not this map on the homology of the relative homology of the modular curve, but its restriction to the actual homology of the closed curve. And it turns out that under this map, the image of the actual homology lies in a slightly smaller group than K2 of the n integers. It lies in K2 of the integers. Okay, so now it actually turns out this map, I mean, you can show it's well-defined quite explicitly. For instance, the relation I've written here, uv equals u, v minus u plus u minus vv, just amounts to the following, you know, sum, you know, 1 minus zeta n to the u over 1 minus zeta n to the u minus v plus 1 minus zeta n to the v over 1 minus zeta n to the v minus u equals 1. So, and both of those quantities that I'm adding are n units. So by the Steinberg relation, they pair trivially, and therefore that relation is satisfied, which is already most of the way to showing this is a well-defined map. Okay. Now, this map is supposed to be Eisenstein in the following sense. So if I consider the Elf Hecke operator, and then I subtract from it 1 and L times the diamond operator of L, if L doesn't divide n. If L does divide n, then really my TL is what, you know, is the operator UL, and I take UL minus 1. So here I just combine them all by allowing, you know, by just setting diamond operator L to be 0 if L divides n. Oh, it should say L divides N there. I think I have L does not divide N written there. Okay. And so now actually I'm going to allow these. If you've seen me give this talk, many of you have probably seen me talk about this before, if not most. So, normally I define the Monin symbols after application of an Atkin-Lehner involution, so I can use actual Heck operators. But here, what I need to use is the dual action of the Heck operators, or the adjoint operators, because I didn't do that. So that's how they're going to act on homology. And then the conjecture that I made was that this map is Eisenstein. In other words, it factors through the quotient of homology by elements of the Eisenstein ideal times the elements of homology. So the quotient of the homology by the Eisenstein ideal. And actually, I conjectured that this map, when I take the induced map on the quotient, it gives me an isomorphism between the homology mod I and K2. So this conjecture is basically proven now. So first there was a result of Fukai and Kato, the first part. The second part's far from proven, though there are results towards it due to Fukai and Kato. But the first part, so if Fukai and Kato proved in 2012, I guess, but the paper was published this year, that the map pi-n tensor, so if I look at the map pi-n on p parts, so these are both finite, so what should I say? I tensor with zp, okay? That's maybe a better way to say it than p parts. So if I take H1 with ZP coefficients and I map to K2 tensor ZP, that this map is Eisenstein. It factors through the Eisenstein quotient as long as P divides N. But the proof for certain P that don't divide N didn't quite work. So by a totally different method, Venkatesh and I proved that pi n is Eisenstein without tensoring with anything, but we couldn't include the operators UL minus 1. So Eisenstein away from the level for L does not divide N. And actually, via sort of a clever combination of the results of these two papers plus proof of level compatibility, basically add P to the level, Lecouture and Wang showed that the map, is Eisenstein sort of away from 3. The only reason they don't include 3 is because Fukai and Kato assume that P is at least 5, and that is because of results of OTA, which they used. But it should.
Could I ask a question?
Yeah. Mm-hmm.
Besides the general proof, if you fix an n, is it easy to sort of check this?
Can you check it? Yeah. So Buziok and I checked. Oh, fix the n, not the l.
Yeah, that's right.
Well, certainly, yes, you can. Right. Yeah, you could check it by computer, of course. Yeah. Yeah.
That's relatively straightforward. That is.
Let's see. Wait, maybe it's not that straightforward. No. Well, you could check it by computer. I mean, if you knew that, say, T2 and T3 generated the Eisenstein part of the Hecke algebra, then you would already know it because we had, but yeah, it's not. Yeah, I think if you have a small enough. Yeah, it's not clear to me that it's that easy to check.
Yeah, that's fine. Yeah, thanks.
Yeah. Okay. So yeah, so in other settings, right, there should also be Eisenstein maps. And so Fukai and Kato and I maybe, I don't know, about 8 years ago, speculated that there should be Eisenstein maps. In fact, I should say people asked me about this first one in many, many talks, or so for over an imaginary quadratic field, the analog GL2 of an imaginary quadratic field, the analog of the upper well, of a modular curve is Bianchi space. So the question is there a map from H1 of Bianchi space to K2 of a Ray class group of this imaginary quadratic field that takes a symbol in the Bianchi space? Cremona defines such symbols in the Euclidean setting to Steinberg symbols of elliptic units. So those are the analogs of cyclotomic units and abelian extensions of imaginary quadratic fields. Over Q, you could try to go from GL2 to GL3. So you have a locally symmetric space for some congruent subgroup of GL3. And on the other hand, so you're going to now compare that to GL2. So you might look at K3 of the modular curve. There are symbols which generate the homology of GL3. It's a nice presentation due to Ash and Rudolph. You can send that to Steinberg symbol of 3 units. There's here that you might have 3 integers u, v, and w, let's say. Steinberg symbol of 3 Siegel units on the modular curve. And over a global function field, actually, you have the possibility of doing this in any dimension. So the locally symmetric space is replaced by what's called a Brouat-Tits building for PGLD. And the modular curve is replaced by a Drinfeld modular variety. Here, if I'm doing something which should be Eisenstein, then we should have, dimension d on the left and d-1 on the right. And again, there's symbols, and at least in equivariant cohomology that Kondo and Yasuda defined. I mean, for d equal 2 in certain global function fields, Teitelbaum already defined symbols long ago. And on these Drinfeld modular varieties in any dimensions, you have analogs of Siegel units, which have to define. So you can take Steinberg symbols of d of them. So one remark is nothing is so straightforward in these settings. If the base ring is non-Euclidean for 1, so in cases 1 and 3, this could happen. These symbols, which I've mentioned, will not generate homology. As stated. Also, I guess I should mention that both 1 and 3 were sort of suggested also through work of Goncharov, who was interested in related maps. Another thing I should say is it's not obvious why any of these maps should be well defined, right? Like you can verify this directly for the homology of modular curves, but in these settings, it's not at all clear. Okay, so let me also mention that in this context, we also have zeta maps, right? So Fukaya and Kato roughly, and this is roughly because I need to invert things, right? Define a map from the homology of a modular curve to K2 of the modular curve. I guess here I should take the modular curve over Q or Z1 over N or something on the right. And it's a Monin symbol to cup product of 2 Siegel units. And actually, I should say Goncharov and Bruneau, they did it p-adically on ordinary parts, and Bruneau gave a construction not inverting much, maybe 6 or something. So, but also, I mean, in the function field setting, one should have zeta maps if I just work with dimension d and dimension d instead of d and d-1. And in both cases, I mean, actually, how Fukaya and Kato proved that pi n is Eisenstein is they composed this zeta map. So Fukaya and Kato, the key thing is that they proved it's Hecke equivariant, not Eisenstein, but Hecke equivariant. But then they composed it with a pullback by a cusp at infinity, a sort of a specialization map that you can define to get to K2 of the cyclotomic field. And that specialization map is, in essence, is very close to being Eisenstein. And so that's how they got the result. And the point I want to make about all of these maps is that they can all be constructed in some form as specializations of Eisenstein cocycles, which I'm going to discuss. So for function fields, I'm working on this with Peter Shu. In the imaginary quadratic setting, which so in zeta maps for modular curves were constructed by Venkatesh and I, and via this method. And in the imaginary quadratic setting, which I'm going to discuss if I have time, is this joint work with Emmanuel Lecoutrier, Shanxi Shi, and Jun Wang. Okay. So So let me say a bit about, very little about motivic cohomology. So if I have a nice scheme over a field, let's say smooth, it has motivic cohomology groups. So in various degrees with a certain, we could call it twist, right? K. Coefficients are ZK if you like, Z coefficients. But okay, so some special cases of this, H11 is the units on your connected scheme, and H0, yeah, here I'm using connected. H0, 0 is just Z. Okay, and in fact, the groups H, N, S, N, I mean, there are cup products on these groups, and both degrees add. So if I have it sort of diagonal, then this I get a graded ring under cup product. And it turns out that, you know, if S is actually the field itself, then these groups are sort of the Milnor K groups of our field. So HNS Fn is Kn of the Milnor of the field. So let me give a very basic case of how these sort of constructions go. Okay, so let's consider GM minus 1, minus the identity, which happens to be P1 minus 3 points. So there's a Giesen sequence in motivic cohomology. I have H1 of GM, so units on GM, and then I have units on GM minus 1, slightly bigger, and then I have H0 of this identity point 1, working over Q. So that's a copy of Z. So I have a coordinate function on GM, and in this H0, I have a canonical element, right? The class of 1 inside this H0. Let's call it E. And well, inside H1, I have elements with residue E, right? Like divisor 1, and for instance, 1 minus Z, right? It turns out this 1 minus Z is the unique element of this H1, which, to make it unique, it has to extend to A1 minus 1 because otherwise, you know, Z, for instance, would, I could multiply it by Z. And it should also be fixed by all trace maps. Okay, so the trace maps are defined as follows. I sort of, oh, this is not quite right. On the right-hand side, it should be Z to the 1 over M in the F, okay? So I take all mth roots of Z, and then I take F of them, and I take the product. So, okay, so it's fixed by all of these. If I do that to 1 minus Z, I get back 1 minus Z. And if I have an nth root of unity, that gives me a point on GM over Q mu N. And I can pull back by this point. And obviously, I mean, when I pull back, I'm just plugging in zeta N, and I get 1 minus zeta N. So, wow, I've constructed the nth cyclotomic, a cyclotomic N unit, right? So, but this is basically how these constructions go. So, you know, if you wanted to construct, for instance, theta functions or Ziegler units, it's very similar, right? You have an elliptic curve over some base scheme, you choose some positive integer. You can either invert 6 like I'm going to do, or take C to be primed at 6. So, so you have an exact sequence here of motivic cohomology groups that I've written out. And this map from H1 of E minus the C torsion to H0 of the C torsion can be thought of as sort of a divisor map. Now, to get some control over the groups, though, we should take trace fixed parts, just like I did on the previous slide. In other words, I have maps for multiplication now by integers prime, push forward maps or trace maps for integers prime to, let's say, C. And, okay, and so I can define the trace fixed part as the things which are fixed by all those push forwards. And then if I look at trace fixed part of H1, it becomes 0, and the trace fixed part of H2 just becomes Z, except for this to remain, the sequence to sort of remain exact, I should invert 6, so it becomes Z1 over 6. So, so that I then have this exact sequence of trace fixed parts over Z1 over 6. This map from H0 to H2 becomes the degree map. And the theta function is sort of the unique element unit on E minus the C torsion. Oops, this N should be C, which has divisor C squared 0 minus the C torsion, which is a degree 0 element, right? A degree 0 divisor. So it's the unique sort of trace fixed element with that divisor. And now again, if I have some N away from C, and now let's say my elliptic curve were the universal elliptic curve over some modular curve, right? So over the modular curve y1 of n. Well, y1 of n comes equipped with, right? It parameterizes elliptic curves together with an n torsion point. So it has a canonical n torsion section. And I can pull back by this n torsion section. So I pull back the elliptic unit, pull back the theta function, I get a Ziegler, right, on the modular curve. So elliptic units are constructed in the same way. If I have a CM elliptic curve with CM by the integer ring, say O of a imaginary quadratic field F, but we have theta functions just as I've described. In fact, we have more of them because we can do the same construction now for any non-zero ideal of O. So let's say C, frac C now is a non-zero ideal of O. I can look at the C torsion, and instead of C squared, I take the norm, the absolute norm of this ideal C. And so now I can again pull back now by any n torsion point on my elliptic curve. And the result is what's called an elliptic n unit. So it's actually an n unit in the ray class field of F of conductor n. So that's the analog of cyclotomic units for imaginary quadratic fields. And, you know, there's some generalization of this to Eisenstein symbols, I guess due to faultings, that works, you know, for any abelian variety of dimension, you know, any abelian variety basically over some base scheme. And you just need to invert enough, and okay, you can get elements, but I will not need them. So let me skip that. Okay, so now we want to make these sort of constructions equivariant for some group action. So let's consider GM squared now. So I want to define some complexes. Okay, so first inside GM squared, I have various tori, right? So if I have two pairs of integers, not both 0, I have a map from GM squared to GM, which takes, let's say, x comma y to x to the I, y to the j, right? And I can take the kernel of this map. That gives me a rank 1 torus inside GM squared. And I can take any collection of such pairs that give me sort of distinct tori, sort of distinct mod torsion. And so distinct pairs correspond to different elements of P1 of Q. And so I take the union of some finite union of, let's say, such tori, and I can also consider the union of the intersections of distinct tori. So that'll be some finite set. And this is a sort of standard thing you can do in motivic cohomology to get a complex. And that is, first I take the complement of the tori, the union of tori inside GM squared, and I consider H2 of that. And then I have a residue map to H1 of SI, but now I'm going to subtract. The union of SI may no longer be smooth, right? But I subtract out the intersections and I get something smooth. So I have units on SI minus TI. And then from there, I have a further residue map to H0 of TI. So this complex is not in general exact. In this particular case, it's fairly close to being exact. In fact, it's right exact. So I consider this as a complex where the degrees 2, 1, and 0, where the twist here, it tells you the degree 2, 1, and 0. And in degree 2, its homology is H2 GM squared 2. And now I could actually take a limit of these things as I subtract more and more tori. And in the limit, I get these complexes are all quasi-isomorphic. And in the limit, I again get some complex, which I'll call K, little k. This sits in a bigger complex, which is this is all you need. But Akshay and I actually use this sort of larger complex, which is the limit over you don't just subtract out tori, you just use arbitrary sort of complements. And so in the limit over the limit of H2 U2, where U is an open in GM squared, is actually K2, Milnor K2 of the function field. And so here, the sequence I have is Milnor K2 of the function field, direct sum over irreducible divisors of units, or the multiplicative groups of the function fields of these divisors, and then one copy of Z for each closed point, right? And now the key thing about this little k and this big K, these complexes, is that they have an action of matrices. So I let matrices with non-zero determinant, integer matrices with non-zero determinant, 2 by 2, act on the right on GM squared in the obvious way. So not on the left, but on the right. And the reason I have them act on the right is that I want to use pullback actions on cohomology, which becomes a left action. Okay. So these complexes are now all equivariant for the action of this semigroup, which I'll call delta. So, right. So inside these groups, which I described, they're all actually in the little k, but they're also in the big complex K. I have symbols. So let me describe these symbols. So GM squared has two coordinate functions, Z1 and Z2. In K0, among the terms, I have the point among the points, the closed points, I have the point 1 again. And the point 1, I have H010. Again, I have a canonical generator, which we think of as the class of 1, and I call that E. In K1, I can take a bunch of things that look like the 1 minus Z I had before, but now what I do is I take a pair of relatively prime integers, A and C. I take 1 minus Z1 to the B, Z2 to the D on the torus, which is the kernel of the map XY goes to X to the A, Y to the C. And I remove the identity. And then, right. And here, the B and D are chosen such that ABCD is an SL2Z. And it turns out this AC is actually just the pullback by the matrix ABCD of the symbol 1, 0 here, where 1, 0 would be 1 minus Z1. Okay, and in K2, I can do something similar. If I have a matrix ABCD, now allow it to be in GL2Z, I can form the cup product of, as written, 1 minus Z1 to the A, Z2 to the C, and 1 minus Z1 to the B, Z2 to the D. This lies in H2, the complement of 2 tori in H2 of that. And again, this symbol for gamma is actually the pullback by gamma of the symbol for the identity matrix, 1 minus Z1 cup, 1 minus Z2. And there are nice formulas for residues, which I've written here. The symbols in K1 all have residue E, and the symbols in K2 have residues which are differences of 2 of these symbols in K1. Okay, any questions? Okay, so here's the theorem. Remember that I had this complex. Let me just go back for a second. I think I went back one too much. Oh yeah, here. The complex K, right? This was right exact. And the kernel of the first map was this group. If I highlight, can you see?
Yeah, we can see fine.
If I highlight, you see the blue that okay, great. Yeah, okay. So the kernel is this, right? So what I'm going to do is make this just like a short exact sequence by quotienting the first term by this kernel. Okay, so let's call that K2 bar. And then, there's
sorry, could I interrupt one question? I should have asked earlier, but could I interrupt this one question? So what you're doing right now Is what you're describing, is this, are you saying this is the same map as your Eisenstein map from earlier, in some sense?
Well, I haven't got it yet. No, but once I'm going to get this cocycle and I'm going to specialize it by pulling back by a torsion point, and then I'm going to recover the same map.
Oh, okay. Yeah. Okay.
Yeah. So, so that first I'm constructing this big Eisenstein cocycle, or actually, so, okay, so, so we have GL2Z acting on our complex, right? I mean, in particular. Well, okay, basically, how am I going to get this? Let me go back to that sequence again. How am I going to get this? So now I have a short exact sequence because I've quotiented this group by the H2, right? And in here, I have a canonical element, which I called E. This E is fixed by the action of GL2Z because 1 is fixed by the action of GL2Z, right? And so, so I just take GL2Z cohomology of this sequence. I have something in H0 of the term I've highlighted here. I get a cocycle in H1 of the quotient here, right? And how do you get such a, well, that gives me a class. How do I get such a cocycle? Well, I do the snake lemma, right? I have an element here. I pick a lift here, and then I take its co-boundary. And then that is going to be the residue of something which took values in this quotient. So let's go back here, right? I have E, I pick a lift, which is this 0, 1, which is 1 minus, I might have said the wrong thing for 1, 0. 1, 0 might have been 1 minus Z2. 0, 1 is 1 minus Z1 inverse on a certain tori, and Z2 equal 1. I take its co-boundary, and then that is going to be the residue of, so that's a co-boundary, but that's going to be the residue of a cocycle, right? And that's the cocycle I want to take. So, so here are some properties. This is a parabolic cocycle. It turns out you can just compute that you can compute everything by residues. So you can, oh, I'll explain it on the next slide. So it's parabolic. It's null cohomologous on all the well, GL2Z stabilizers of elements of P1Q under its sort of right action. It satisfies an explicit formula that I've written down here in terms of the symbols in K2. So basically, this uses the Euclidean algorithm very strongly to sort of break up a matrix as a sum of matrices in SL2Z, essentially. I've written down what such a sequence is. You can always find one. So it starts with sort of 0, 1 and goes to B, D if the determinant's 1. Okay. And it's also Eisenstein in the sense that we can define Hecke operators attached to double cosets of, let's say, say TL is attached to the double coset of L001. And then TL minus L minus pullback by multiplication by L of this cocycle is 0 in cohomology for every L. Okay. So here's a proof, sort of. Okay, I said why theta exists. Everything else is computed on residues. The boundary, so the residue of, because the residue map's injective because I've modded out by the H2 of GM squared. So the residue of this theta vanishes on the stabilizer of a particular element. And that's really all we need because all parabolics being conjugate, you know, on all other parabolics, it's a co-boundary. Okay, to see the explicit formula is just a matter of, we want to say that this quantity equals this quantity. And then I had this, I take the residue of the sum, that's the sum of the residues, and they were these differences. And then we have telescoping, and then it just reduces to this, which is what this was. And finally, the reason we have the Eisenstein property is sort of that the connecting, because delta acts on my complex, it's a delta equivariant complex, that gives me, it means that the connecting map is actually Hecke equivariant. So the class of theta is constructed using this connecting map, which I've written down here, ascending E to the class of this theta. And so to compute that TL acts on theta as described, we can check it on E. And so what does TL do to E? TL is the sum of the pullbacks by all the matrices, you know, the coset representatives on whichever side for L001. So here those are like Li01, I0 through L-1, and one more matrix. But the point is the pullbacks by these things of the identity are all the different cyclic subgroups of order L inside mu L squared, right? Inside the L torsion in a GM squared. And if you take that sum formally, well, okay, if I sum over all the cyclic subgroups, I'll get all of mu L squared, but I'll be overcounting the identity for because I have L plus 1 subgroups, right? So I'm overcounting it by L. And of course, mu L squared is the pullback by multiplication by L of the identity. And so I get L plus pullback by L E. Okay, that's all it is. Okay, so now I want to specialize. So if I have an open in GM, so there's a bit of a tricky point with specialization, and that is that, you know, as I've defined it, if I look at my big complex K, what I have is K2 of Q GM squared. Well, that has no points other than like a single point, and I can't sort of specialize at a torsion point on that group. So I need to work with smaller H2s. So if I have an open in GM squared that contains, say, 1 comma primitive nth root of unity, then I can define a pullback on H2, right? I have a pullback map from H2 U2 to H2 Q mu N2, which I mentioned earlier is Milnor K2 of Q mu N, and Milnor K2 and K2 are the same thing. Okay, so can I do this? Well, okay, so the value of theta at a matrix gamma A, B, C, D lies in some quotient of H2 of some open. What open? Well, it's GM squared minus 2 tori, S01 and SBD. And so what we want is 1 minus theta n is not in these 2 tori. It's not ever in S01 because the second coordinate is not 1. And it's going to be in the second one if and only if n divides d. So what we need is that in our matrix, that n doesn't divide the lower right-hand corner. Then we can specialize. So, so the idea then is to restrict to the subgroup gamma naught of n, now of GL2Z, but sort of usual condition for gamma naught of n, that C is 0 mod n, which forces then D to be relatively prime to n. Okay, so we'll restrict our cocycle to that. There's a little tricky point. So I could then pull back, right? And then I'll land in the quotient of K2 of Q mu n by something, the specialization of H2 GM squared, but that's a little too big. So what we do at this point is we consider trace fixed parts, and it turns out the trace fixed part of H2 GM squared is generated by the cup product of the 2 coordinate functions, or the negatives of the 2 coordinate functions. So we sort of replace K2 by its trace fixed part. The specialization of the cup product of these 2 coordinate functions is just the Steinberg, well, we just plug in 1 comma zeta n, so we get the Steinberg symbol, or the cup product of -1 and minus zeta n. Turns out this is order 2. It's -1 if n is odd, and it's 0 if n is even. So it's some very small group. So now our specialization now lands in K2 mod this group of order 1 or 2. And again, it's still a cocycle, but now I need to say how the group acts here. So a matrix A, B, C, D in gamma naught of n acts as the Galois element sigma d, where sigma d acts on an nth root of unity by raising it to the dth power, right? It's the element corresponding to d in the Galois group. It satisfies an explicit formula that just comes from specialization, right? The specialization of my symbol ABCD is 1 minus zeta n to the B, 1 minus zeta n to the D. So I get sums of such cup products, which it's parabolic. This is not quite as obvious anymore because of what I've done, but it's true. And now it's Eisenstein, but now only away from the level. You see, when I restricted to gamma naught of n, TL became UL, and also, you know, I'm specializing at this n torsion point, and then the TLs, you know, for L dividing n will not commute with the specialization. So, but what we do have is that if the TL for L not dividing N commute with the specialization. So most of these properties pass to the specialized cocycle. Okay.
Sorry, what does parabolic mean?
Well, parabolic, yeah, it's a fairly strange definition that I took. It means that its cohomology class restricts trivially to H1 of various parabolics, but these parabolics are actually right stabilizers of elements of P1 of Q. For that.
This is like hospital somehow, something like that.
Yeah, like cuspidal, right? Yeah, like so this is going to give me homology of the closed curve versus homology of the open, basically. Yeah. So when we'll see in a second when I specialize what this gives me. I mean, when I restrict to gamma 1 of N. I think it's the next slide. So let's see. Yeah, so now I want to restrict theta N to gamma 1 of N, right? Gamma 1 of N here in GL2Z, I just take D to be 1 mod N. But I could also restrict to the usual gamma 1 of N in SL2Z. And the point is that, on gamma 1 of N, it's now a homomorphism, right? Because the action, remember, of the matrix was through the lower right-hand corner, the Galois element sigma D, where I raise n through the unity to the dth power. So now the cocycle becomes a homomorphism. So I get a homomorphism from gamma 1 of N to this K2, this quotient of K2. So it factors through the abelianization of gamma 1N, which is H lower 1 of gamma 1 of N, which is H lower 1 of Y1 of N, right? The open modular curve. But because it's parabolic, that's saying exactly in this case that the map actually factors through homology of the closed modular curve. That's what the parabolicity gives us in this case. And the fact that this gamma 1 is for GL2 and not SL2 means that this map actually factors through the quotient by complex conjugation. So we get a map from the homology of the usual modular curve mod complex conjugation to K2 mod this group of order 1 or 2. And it turns out that if we invert 2, so I tensor with, which I did in the beginning, right? And I take plus parts, say, I get exactly the map I defined, pi n I defined earlier as the restriction of this explicit map to the homology of the closed curve, right? The explicit map was defined on homology of the closed curve relative to the cusps. And from the Eisenstein property of theta n, I get that this map pi n is Eisenstein away from the level. And I'll just note that you might think, well, but this Eisenstein property looked different because it was TL minus L minus pullback by L, not TL minus 1 minus L diamond operator L. And that has to do with the fact that the operators are different. So the operators I was taking are dual to the operators I started with in my initial description. They're the usual operators instead of the dual operators. And so when you do the translation from usual operators to dual operators, which I've written here, TL star is L inverse TL and L star is L inverse, you get back the relation I had in the first place. Okay. So, okay, any questions?
Maybe, sorry.
Mm-hmm.
I hope this isn't completely stupid, but
Yeah.
So that explicit complex you had earlier,
Yeah.
so that thing is something quite general in Pullett K theory, I guess. Is that right? Where you
Yeah.
points of dimension D to D minus 1, etc., etc.
Right, right, yes.
So that's a kind of very conceptually general thing. So is it correct to say that your Eisenstein map comes from that followed by a specialization in a very subtle way?
Yes, exactly. Yes.
Okay, great. Now I think I've finally understood your map.
Okay. Yeah. So I'm going to do another example of this. I've written a lot of slides, but I didn't go. I'll sort of give an overview of the current work. Okay. So the current work is on products of 2 CM elliptic curves. Okay. To get a similar map in the Bianchi setting goes to products of elliptic units, but we don't quite get that. I'll explain. So again, as you said, it's quite a general thing. We can do this for a square of an elliptic curve, for instance. Maybe actually, I should have done this for products of two elliptic curves because that's what I'm going to use. Okay, but I mean, so I could also do it for product of two elliptic curves, right? I have a sequence like this. It's a complex. It's very far in general from being exact. So this is K2. I have K2, K1, K0. Those are my degrees. In the ith degree, the homology of this complex is the 4 minus ith cohomology of the square of the elliptic curve with the 2 twist. But it turns out if I trace fixed parts, these groups all vanish outside of H4. So instead of being, so if I take trace fixed parts, and now I have to make this work, I actually have to invert 30. I get an exact, so let's let Z prime be Z in, with 30 inverted. I get an exact sequence like this on trace fixed parts. And so what is this map? This is essentially, right, this is essentially a degree map, sums of points, right, with their degrees. Okay, so I have a sequence like that. So instead of the sort of right exactness, now I have like a left exactness. Okay, this also works for products of two distinct elliptic curves, which I'm going to use. So the setup here for CM elliptic curves is I have an imaginary quadratic field. It has an integer ring O, and I have an indexing set 1 through the class number H. And I'll choose ideals representing AR, representing the class group for R in this indexing set. I need some auxiliary ideal F because my elliptic curves are going to be defined over the ray class field with conductor F. This F has to have not be so small, but it has to have the property that the units in O inject into O mod F. And okay, and then I can define certain elements of the Galois group of, say, L over F, which is Artin map applied to the inverse of this ideal AR. And I also need some auxiliary C. Okay, so now the key point is that I have non-isomorphic elliptic curves. How many isomorphism classes of CM elliptic curves by O do I have? It's exactly the class number. So I have E, R for R and I. I can choose them to be defined over the ray class field with the very nice property that the R torsion, if I take the field of R torsion over F, this is actually abelian over my imaginary quadratic field. Right, and I'll choose them also so in this way that I've written here, and I'll choose them to be conjugate to each other. So ER is the conjugate of E1 by sigma R. Okay, and ER, the C points are C mod the lattice AR. So then, you know, like homomorphisms from ER to ES, isogenies from ER to ES for R and S and I are exactly, so sorry about the two equals, this thing AS AR inverse, which I'll call ARS, right? It can be identified with that. Okay, and later I'll need some point on, N torsion point on each of these things, but I don't need that yet. Okay. So, okay, so now what I'm going to do is I'll take pairs of these CM elliptic curves, right? So I have EI1 and EI2. I take their product. Let's call that script EI. So to a point in I squared, to a tuple, a pair in I squared, I associate a product of two elliptic curves, EI, and then I have an associated complex, which I described earlier. I take its trace fixed part. Okay. And so now these complexes, well, now I have a bunch of complexes, so I should have maps between them. And how do I map between them? Well, I define this thing delta, this set of matrices in M2F, delta ij, where the coordinates are chosen inside, you know, these things here, such that, you know, by the description of the homomorphisms I gave here, right, from ER to ES, such that, you know, an element of delta ij maps EI to EJ. And then by pullback, I'll have a map on complexes from the jth complex to the ith complex. And so the group I'll then be interested in is those elements in delta II with invertible determinant. Okay, let's call that gamma I. So that now acts on the ith one of these complexes. And again, the setup is very similar to what I had before. This looks like what I did for elliptic units, but now there's a square here. So I take the norm C squared times 0 minus the C torsion in this product of two CM elliptic curves. This thing is fixed by the action of this group, and I have a connecting map. It's also degree 0, so I can apply a connecting map to it and get an element, a class of some cocycle. Right now, one might say, okay, I have a class, not a cocycle. So how do I get a cocycle? And there's a way to do it. Here's a way to do it. This is something in K1, which maps to ECI. And this is about as simple as you can get. It doesn't look very simple. The point here, this exterior product means I have a theta function. This is a theta function as defined earlier. And I take the function on the square, which is like supported on this C torsion here, right? And the first, so it's determined by the first coordinate as long as the second coordinate's in the C torsion, otherwise 0. And so similarly here, the awful thing about this choice of representative is we verify, unlike in the GM squared case, sort of this is fixed by one parabolic, this is fixed by an opposite parabolic, and the whole thing is fixed by no parabolic. So now my my class is not parabolic. Okay. Oh well. Okay, we can define Hecke operators. If I have an element of this thing delta ij that I defined, I can define Hecke operators, and then I can define Hecke operators associated to matrices. So the thing I define that in some way. For an n, I choose I and k such that like n times each of these ai u k u's is principal. I choose a generator, and I use this generator to sort of define the Hecke operator. In this case, the Hecke operator for pullback by n. I also have a Hecke operator Tn, which looks like this. And then the collection of classes that I've defined. So now, yeah, so the trick is these Hecke operators don't preserve the complexes, right? They map one complex to another. So what I do is instead of looking at a single one of these classes, we take the collection of them all together. And we can look at, so like the tuple of them. And we can look at how the Hecke operator acts on the tuple. Oh, this should be a P. I don't know what I wrote here. This is a P, and this is a C. Okay, and then it's Eisenstein, right? If I take the collection. And again, this reduces just to checking this on this element EC, which in turn reduces to just checking it on 0. And then the proof is exactly the same as the proof I gave for GM squared. So again, we can do pullback if we restrict to a certain group gamma naught. We sort of fix nice end torsion points to do this. One tricky point is that my elliptic curves were defined over the Ray class field of conductor F. So a priori, my specialization lies in some bigger Ray class field than I'd like, but it turns out that the values of the specialization on the values of the cocycle actually lie in K2 of the Ray class field I'm interested in. So I don't need this auxiliary F. It's sort of independent of F. And so our theorem is that this cocycle is Eisenstein away from the level. If I change C, so if I have a C and D, I can compare these cocycles in this way, which comes from the comparison of the elements E, which I used to define them. This is really tricky, actually, to prove. And in fact, it's integral in a certain sense, or close to integral. It lies in something smaller than K2 of the Ray class field. And one might ask, okay, I have some relation like this. Is there a single like theta n that gives all of these thetas with a C? This is something that you have for Siegel units if you allow denominators. And under certain conditions, so either P doesn't divide the class number or P doesn't divide n squared, then the answer, if I tensor with ZP, is yes. So there is such a cocycle or collection of cocycles with this property, right? That sort of this one class, collection of classes gives me all the cocycles. Okay, so now, how do I get maps on Bianchi space? So one thing I want to point out is I just defined h squared cocycles, right? H squared classes. And now Bianchi space, right, like, which is the quotient of the upper half plane C cross the positive real numbers by this, let's say, congruent subgroup gamma 1n is, right, like that's a connected component of Bianchi space for a given gamma 1n R. How many connected components do I have? I have h of them, not h squared, right? So what I do is I only look at the tuples where the second coordinate is, say, 1, r comma 1, and I'll just call that gamma 1n r. I look at, so the condition for being in gamma 1n is that D should be a unit mod n. And I then have this Bianchi space, which is a union of these like h different components. And the restrictions, again, of these cocycles to gamma 1n are homomorphisms. And then the same way, we get a map from h lower 1 y1n to k2, which is Eisenstein, again, away from the level. But now, so one might ask, I should say I wrote this Eisenstein as the Heck operators I defined are sort of non-standard, so there's some translation to actually getting this. One might ask about parabolicity, and we actually do show it's parabolic outside of certain eigenspaces under a condition on the level, but I think hopefully that will be extended in future work. So even though, what I would say is that even though the big cocycle isn't parabolic, I do believe that the specialized cocycles, the specialized maps, that these maps themselves are parabolic and should satisfy explicit formulas. Okay, so that's what I wanted to say. Thank you very much. Hello? Let me stop sharing. Oh. Hello?
Can you see us?
Yeah.
Alex, he can't hear you because you're too far away from him.
I think Alex has run off to the control room.
Oh, okay.
You should be able to see us
Oh, he's
now.
back.
Can you see us as well as hear us?
Yeah, I'm trying to get you bigger though. Yeah.
Be careful what you wish for.
Yeah. Well, I can't get. Oh, maybe I can. I can't get you bigger, but I see a very tiny version of you. Yes.
Oh, that's for yeah. Maybe that's sufficient. But yeah, does anyone have any questions for Romyar?
So what's the overall goal of, is it to construct elements of K2 of modular curves? Sorry, of these